Hello, everyone, and welcome to the webinar. The NAGT webinar series is your one-stop shop for increasing our community's capacity in Earth education. Webinars in this series feature novel and innovative work in Earth education research and pedagogy, new teaching materials, and the classroom and professional experiences of people just like you. The webinar series is free and open to the public, and we encourage you to invite your colleagues to attend and join the discussion. Before we get started, please take a moment to review the Zoom controls on the screen. We do ask that you leave your microphones muted and cameras off. If you have questions and comments along the way, we encourage you to enter those in the chat box. The presenters and staff will be monitoring the chat, and you can also use the reactions tab to give nonverbal feedback. Also, a reminder that NAGT webinar participants are expected to abide by the NAGT Code of Conduct and information the Code of Conduct, which applies to all venues, events, and forums associated with NAGT. Please read the full NAGT Code of Conduct at the link I just put in the chat for more details. On this screen is a link to the webinar series where you can find the webinar schedule, an archive of past events, and information on our sponsoring projects and programs. You can also find slides, resources, and recordings of every webinar through the webinar activities pages. Today's webinar is entitled Core on Shore, a virtual tour of IODP's Gulf Coast repository. Our presenter is Laura Girton from Penn State. And with that, I will hand it over to Laura to launch into the webinar.
Excellent. Thank you so much, John. And hello, everyone. Hello from the campus of Texas A&M University, where I am currently located. Again, my name is Laura Girton, and I'm a faculty member at Penn State Brandywine, located in Media, Pennsylvania. I teach introductory level courses for students in the first 2 years and for non-STEM majors. And I am, by training, a marine geologist. And so even though I do a lot of work with pedagogy and creative teaching methods, in my heart, of course, I'm a geologist and always love any opportunity to get out into the field. And I had the amazing opportunity to sail on the scientific ocean drill ship, JOIDES Resolution. And what I'm going to talk about today is not just the ship itself, and I'll give you a little bit of background about JOIDES Resolution, but I wanted to talk about where I am now and why I'm here too. So I am at the street address 1000 Discovery Drive, and I can't think of a better place to actually be the Science Operations Center for JOIDES Resolution and also the home to the Gulf Coast Repository. And I'll talk about what all those are in a sec, but part of my motivation for wanting to give this tour to each of you is I think it's important for us as instructors to also think when we're showcasing and framing scientific expeditions or fieldwork to students, that the work doesn't end once we leave the field. I can't tell you how many times after spending 2 months on JOIDES Resolution, people have said to me, well, 2 months on the ocean, that was such a long time. So now you know everything, right? Now your work is done. And as we know, it's just beginning. There's so much more work that we can do, samples we want to collect and look at again and relook at, and more connections and collaborations. And so hopefully this tour can also be a reminder to each of us that we can take a step back and scale out a little bit to help our students understand the bigger picture of doing the process of science and really learning about planet Earth. So in terms of this process and how did we start learning about what's at the bottom of our ocean? Well, when we think about scientific ocean drilling, I'm just going to share a couple of photos with you for us to think about where did it begin. And this ship is really the start of it. And hopefully you can see the caption underneath too. This is the first ship. It was a Navy barge in the 1960s. It decided to go, went south of San Diego, off of Mexico, and did the first drilling operations in the deep sea without being anchored or tethered to the bottom of the ocean. So there was this big question, Project Mohole too, you might have heard of that. This is that operation. So the idea of, can we actually drill to that crust mantle boundary? So we're still not there yet, got quite a ways to go, but so much came out of this expedition in the 1960s where we learned a lot about how, first of all, that we could be in 12,000 feet of water and drill down 601 feet and actually be able to bring up material onto a vessel. We learned about the technology that's called dynamic positioning, where for this ship, it was only 4 motors that were controlled to try to keep the ship within a 600-foot radius. So therefore, it didn't drift too far where the pipe would bend and break. And again, I hope you can see in the caption there, John Steinbeck was on this operation. And he was an amateur oceanographer. And it's amazing that not only did we have him be able to participate in this first attempt of trying to drill down in the Mohole, but having him and his writing abilities and his connections and communications, an article got in Life magazine. And it created such excitement and such a chatter that even the president at that time was sending messages back to the scientists saying, this is incredible. We've got this space race that's gearing up. And so now we've got this race in our ocean, and yay to the scientists to be able to move this forward. So this issue of Life magazine is available through Google Books if you want to see it. And John has the link for that. Maybe he can put that in the chat. He also has the link to an article that talks a little bit more about the CUSS-1, which was the first ship that was the one that was doing those initial operations. And so it's really a fascinating history, and sometimes fun to give students that context too as to where we came from. Well, 1968 was a magical year because that is the year that the scientific drilling vessel Glomar Challenger was launched. It was built and launched out of Orange, Texas, and it did its very first mission in the Gulf of Mexico. And immediately from this vessel, we started seeing some significant scientific discoveries. And from the first leg, we saw that we have salt domes in the offshore, again, being able to use dynamic positioning systems. So we've got some important scientific finds, important economic finds, and then Glomar Challenger continued into the Atlantic Ocean, started going through our ocean basins for 15 years. After 15 years, then we hit a pause, and we had a new vessel that came on board, which is the one we're still using today, JOIDES Resolution. I will say there is another scientific drill ship that is on the water, owned and operated by Japan. It's called the Chikyu, and we also have mission-specific platforms that go around. So there is opportunity for us to collect more material and more information. But then what do you do with all that material? What do you do with all that core material that comes up from the ocean? Well, John Steinbeck was so intrigued that he, in the Life magazine article, it actually describes how he was looking at all this basalt that was broken up, and he took a tiny piece of it and he put it in his pocket because he wanted to bring it home as a souvenir. And he felt so guilty about it that he actually put it back in the core. So we do not take pieces of rock that we collect and drill from the ocean floor and put them in our pockets, but instead we put them in repositories like this. So what I'm going to do now is I'm going to go ahead and I'm coming to you with an iPad that is attached to a monopod. And I'm going to walk into the building here. I'll show you a little bit of the displays that are here in the front, and then I'll take you actually to where we store the core. We'll take a look at some of the equipment, talk to at least one or two of the scientists that are here, and hopefully I'll be able to answer your questions along the way too. So I'm gonna flip this camera around and we will enter 1000 Discovery Drive. So JOIDES Resolution, being the scientific ocean drilling vessel that's part of the International Ocean Discovery Program, has many nations that are participating and that are part of it. The United States is the operations center for it, but it's registered in one nation and it's owned by another nation. But here it is, obviously the scaled down model, 470 feet in length. That's about the length of 10 basketball courts. You can see the derrick that's here on the top. Approximately 190 feet above the waterline there, about the height of 20 basketball hoops. And it's out there. It is out there all year round. It operates 24/7. So the crew that's on board, the scientists that come on board are always out there collecting new material and new information about the ocean floor. If you want to know more about JOIDES Resolution, I gave an NAGT webinar earlier this year about from the ship itself and took an iPad around. So there's lots of great information you can get there. What's nice in the lobby here of the building too is that they have some core replicas on display. And I say replicas because we actually keep the actual cores in the refrigeration unit, which we will go into in a little bit. But this is just striking too, right? You can see all the variation within this material. And these replica cores, you actually can request. They are on loan. So that's something, if you're interested, going to the Gulf Coast Repository website. This front one here is always a fun one to show tours, especially for younger kids. When you say dinosaurs and you say dinosaur time, impact, after dinosaur time, and how visibly before and after may look the same consistency, but then you can talk more about microfossils and planktic forams and the differences that happen there. This is a core that contains PETM and so forth. So we've got a lot of options from what we've learned from the oceans to be able to then share that with others. As I continue to walk around to another area of the repository, I'll just pull this map up to show you. Every dot that you see on this map is an area that's been drilled either by Glomar Challenger, by JOIDES Resolution, or by the CHICU. And again, we've been doing this since 1968. So that's, each of the colors just represents the program that was done. And I'm going to call your attention, if you could see those 4 pink dots between Africa and South America. That is for the South Atlantic transect that I was on earlier this year. So let me go ahead and stop the share and give you just an overview of the South Atlantic transect, a very brief overview. You'll see 4 expedition patches here, and that's just because back, the expedition was initially supposed to launch in 2020. We know a lot of things happened in 2020, and so some engineering expeditions went and tried to set us up so that when it was safer, we could get our full suite of scientists, along with the technicians, along with the crew, to get out there to accomplish our scientific objectives. So I'm going to come a little closer to this one so you can see what we were doing. So we started in Cape Town, South Africa. We sailed to the west. We went across the mid-Atlantic ridge, and we drilled cores in a transect that was perpendicular to the ridge. We drilled through the sediments, and we also drilled into the basalt. We wanted to both. So one of our objectives was actually looking at the rock itself, and trying to understand. Now, we know it's older the further away it gets from the boundary. We share this with our students as well. What we don't have a really strong understanding on is, how do these rocks age? What's happening chemically and physically as we get further away from the ridge? And so that was one of our objectives. You can see these arrows here again, the cycling and the movement of hot fluids. What is that impact? And then we also had a microbiology objective on this expedition too. And that's what this little magnifying glass is signifying here. So we know there's life in the water column. We know there's life in the sediments. There's life in the rocks as well, but we don't have a good understanding of that either. And how do these assemblages change over time as you get further away from the ridge? And what's happening with the impact of fluids? So lots of questions. And the only way we could get the answers to these questions was by getting the actual core material. So my expedition sailed through the months of April and May of 2022. We drilled down through the oldest material. So we went down about 61 million years in age, not quite dinosaur time. And we drilled the youngest core. Then the 2-month expedition after mine filled in the gaps that we had in the middle. And so what do you do with all this core, right? So now once you collect core, whether it be from Glomar or currently from the JR or CHICU, there are 3 core repositories that exist in the globe. Again, this is an international partnership with groups coming together. So if a core was drilled in the Gulf of Mexico or the Pacific or the Southern Ocean, those cores come here to Texas. They go to the Gulf Coast Repository. So the very first cores from DSDP1, that very first leg, are actually here in Texas. If the core was drilled in the Atlantic Ocean or the Arctic Ocean, then those cores will go over to Bremen, Germany, to that core repository. And if they're from the Indian Ocean or the westernmost Pacific, then they go over here to the Kochi Core Center. Now, I just shared with each of you that I was on the South Atlantic transect and I was in the Atlantic Ocean. So why am I in Texas? Because my cores should be in Germany, right? Well, they actually got shipped here first. So we have the sediment cores and our rock cores. And we're doing some more scientific work on it. We're doing some analyses with equipment that is here that is not in Germany. So we're running those samples. And currently, why I'm here is I am with part of our science party where we're doing what's called a sample party. So it's funny what I've been doing tours this week for elementary school groups, and I've had my squid party hat on looking for a party. Again, we need to be careful about some of the terminology we use in the audiences that we speak to. So what is a hard rock sample party? And we have our petrologists here. We have our physical property specialists, the people that have already spent 2 months on the ship looking at this material that we just brought up. But then once you go back to your institutions, you start doing some work, some analyses, you realize you need more samples. You need to connect with the colleagues more. So several months after an expedition, the cores they kind of come back out, we get back together and we discuss and share and together figure out how to sample more material, but not oversample the cores either. So what I'm going to do now is I'm going to start walking into the actual repository. So I'm going to switch the camera on my iPad here as we go through. So here's the sign, Gulf Coast Repository. We've got several places where material is stored. I'm not going to open these freezers, but it wasn't just my expedition that had a microbiology objective. There's other ones that have as well. So when those microbiology samples are collected on the ship, they immediately are frozen. And you can see here the minus 86C. So yes, that's minus 123 degrees Fahrenheit inside these freezers. And that's where the samples stay until scientists are ready to work on them. We don't do a lot of microbiology analysis. We just prepare the samples and package them up on the ship because the ship does not have a clean room. So you want to use the cleanest lab possible if you're going to do that type of work. This cart here, I'll just stop a little bit. Back when we started with scientific ocean drilling and we weren't sure how to do it, how do you break through material? I love showing the example. So these types of drill bits and drill cones are what we use now, but very fascinating designs of what people came up with in the past, trying to figure out how do you break through that rock? And then once you do, how do you get it back to the surface? So a lot of great history into the whole process of scientific ocean drilling. All right, so in front of me are 2 freezer doors. I am going to open them. There's actually 4 freezers here. They're all connected to each other. And I'm going to stay right by the door because the wireless does not go into the freezer very far. Or I'm sorry, the refrigeration. I need to say refrigeration because even though it's typically in the 80s outside in Texas right now, it is 40 degrees Fahrenheit in this refrigeration unit. 40 degrees because that is the average temperature at the bottom of the ocean and where this material was collected from. And so you see that we have a core going down there, and then we have aisles and aisles and aisles. Again, this is just 1/4 of the entire refrigeration area. It's 15,000 square feet of space. It is filled with 150 kilometers of core. It can only fit about 15 kilometers more. This repository is almost full. Now, the JOIDES Resolution is currently in the Atlantic Ocean. It's going to be there for the next couple of years. So all the new core will be permanently stored in Germany. So that's good. We've got some time to be able to work out the space issue. But as you see here, you've got some what we call D tubes, these long tubes. And those are the sections of cores that come up. Some have black caps and some have red caps on them. And that's because when the core comes up from the ship, the first thing it does is it gets split into half. Half of the core we call an archive half, and half is the working half. So the archive half gets those red caps. So the red caps are, we don't touch it, we can look at it, but we don't sample from it. We try to keep as full preservation as possible in half the core, but these black caps here are the working half. So on the ship, depending upon what the material is, you'll get your micropaleontologists that'll start collecting that sediment to be able to start identifying the microfossils that are in there. Your paleo magnetics people are going to be drilling plugs or collecting cubes. Your physical properties people will be doing the same. So the black tube, it contains the core that has been sampled from, but again, that stays here. Even after samples are collected on the ship, once the expedition comes out of a moratorium period, anyone can request samples from the Gulf Coast Repository or Kochi or in Bremen. So these there's some red bins here and some gray bins in the back. That is what we say is residue material. So that's material that has already been sampled or kind of comes back. Again, no one gets to put a small piece of basalt in their pocket from the deep ocean. Everything is cataloged and archived and accounted for here. So if you are a scientist interested in any information from any of the past expeditions, you can make a request online and samples will be sent to you. For example, if you want to look at some of the thin sections that were created from an expedition, then you can request those, but you only get to keep them for a year. They do need to come back here as well. The Gulf Coast Repository gets approximately 100,000 requests from across the globe every year for people looking to study from all of these materials that have been brought up. All right, I'm going to step out and warm up a little bit. The next thing I'm going to do is I'm going to walk through one of the other sections here of the repository and walk by some more core material. In the back of this refrigeration unit is our XRF lab. And I want to get to the XRF lab. Just so you know, the wireless does not exist in the middle of this refrigeration unit though. So I'm unfortunately going to be dropping out very briefly, but then I'm going to come right back in and we will see what's going on with XRF collection right now. And you can see more of those gray and red bins here. Here's some more. These are older. This is leg 17. You see it's just white caps here. This is before they went to the red and black convention for these D tubes. But okay, here we go. Now walk fast. John, can you let me know if I'm back?
Yep, you're back.
Perfect, yes. It's a chilly walk, but it's nice to get to this back room. So what I'm gonna do is flip my camera now so you can see what this back room is. It does double duty. So this is a machine shop. And this is where a lot of the instrumentation that goes on JOIDES Resolution is built and constructed, with each expedition having a different mission and objective. Sometimes there's specific tools that you need. The other thing to keep in mind too is that when you're out on the ocean, when you build something, you want to make sure you have the spare parts with you. When you're on the ship, you can't run to Lowe's or Home Depot to actually get any backup material. But there are engineers and technicians on the ship, as well as computer programmers. There's the chefs, there's the doctor. It's not quite a floating city, but you've got people with a lot of different expertise that are out there doing work. And we have a couple of people that are working on these XRF machines. There's one on this side, one on this side, and Adrian is going to talk to us a little bit about XRF and explain what's going on. So, hi, Adrian.
Hello, everyone.
Do you want to introduce yourself?
Yeah, so I'm Adrian Lamb. So I'm a postdoc at Binghamton University, and I'm here with my PhD student, Ravi. He just started with me this semester. So, and I'll be transitioning to an assistant professor next year at Binghamton. So what we're doing here today and through the weekend is XRF core scanning these cores that's going to be used for Ravi's dissertation. So essentially what we're doing with XRF, it shoots these X-rays, this energy, into the sediments themselves, and that excites these little atoms that are in there, and it reflects energy back into the sensor as it shoots those X-rays down. And what this machine is doing is measuring that excitation energy, and it can correlate that excitation energy to different elements that are contained within those sediments. So what we can do then is kind of qualitatively assess what amount of different elements are in the pores themselves in the sediments. We can also do this with hard rock. So we're going to do this with some of those C4 basalts that we drilled later in the week. So this can tell us a lot of different things. It can tell us about the strength of the winds that blew over these pores or over the ocean where these pores were drilled. It can tell us about productivity in the surface ocean. So how much organic matter or stuff was fluxing down to the seafloor. All types of different things. And there's one interval that we're really interested in. It's called the Middle Miocene. So this was a time interval from about 17 to 13 million years ago. And this is a time when Earth got really warm So that's called the Miocene climate optimum. Earth heated up to about 500 parts per million CO2. And there's some ranges in the literature where that differs. It could have been a little warmer, maybe a little cooler, but that's right around where we're sitting. It's targeted as an analog climate state for what our climate might be heading into in the next coming decades, right? So this is an interval of time that geologists and climate scientists are very interested in. We'd like to reconstruct how the Earth worked during that time, because it may be how our Earth is going to behave, our Earth systems may behave in the coming decades. So what we do in my lab is reconstruct surface ocean currents and atmospheric processes, so like how strong the winds were blowing in what direction, under these ancient warming events, to infer how our Earth may operate in the decades going forward and how that may affect ocean plankton, so these tiny little protists that live in the surface ocean. So what we're scanning right now.
Can we take a look? Or
Sure. Yeah.
So again, here's our X-ray fluorescence machine. We do not have this on the ship. A little too large, a little too sensitive to work with. So, so that's why these cores will stop here. They also don't have this set up in Germany either. So even though, again, these cores were drilled in the Atlantic Ocean, they're here for us to do some of the initial analysis on.
Yeah. So what I want you all to pay special attention to is how light these sediments are. So they have like this tannish color to them, and that's because there's so many microfossils that are contained in them. And these microfossil tests or shells are made of calcium carbonate, so same thing as seashells. So they're very white and we're very reflective. And when they occur in great abundances in the sediments, that makes the sediments very light in color. So there's two major climate events that we want to investigate within these sediments that we're scanning right now. So the Miocene climate optimum was the one I was telling you about. But then as the Earth cooled back down, Antarctic ice grew very large. And that really was the major step that took Earth from like a pool house world to more of an ice house like we're in today. We have major polar ice at the poles. And that step in cooling is called the mid-Miocene climate transition. So these sediments are prior to the onset of the mid-Miocene or the Miocene climate optimum. So Earth was warm but not so hot. But what I want to do now is take you over to the table.
And I'll just mention, I don't know if you saw that there's the red caps in the back, and I already explained red caps are hands off. We're not supposed to do anything, but archive halves, because X-ray fluorescence is a non-destructive process, we actually can do this on these complete sections from the archive, which is wonderful to be able to get all the data.
All the data. We want as high resolution as we can go. So I want you all to pay special attention. These are the cores that are the youngest. So this core was drilled below the one that's being scanned now. This core was drilled below this one, and this core below this one. Now I've skipped a few cores in between these, but then these are even older. These are the beginning of that Miocene interval that we're very interested in before the Earth got very hot. So what I think is happening is that these sediments, notice how they're very light in color. They're that tannish color again, so lots of microfossils. But then notice how these get very chocolate brown. They're like the exact color of a Tootsie Roll. So I've been calling these the Tootsie Roll sections.
That's great.
Yeah. So what I think happened is the ocean chemistry, as the Earth got very warm, it completely changed. So maybe the bottom waters of the ocean became very acidic. And when those bottom waters become acidic, that essentially acidifies all those microfossil shells that are contained within these sediments and causes these sediments to be darker in color. And that darker color comes from all of this dust-blown sediment that comes off of the continents. So these are things like, I don't know, continental rocks like you would find in your driveway, granites, gabbros, maybe some limestone, stuff like that. But again, they're very dark in color because they lack so many of those microfossils. So it's very neat because we can actually see these climate transitions in the cores and their colors and how they change through time. So we're actually like really excited about this, to be able to see these events in the cores and the sediments themselves.
This has been a great summary, Adrian. Thanks. And what I want to do is I'm going to flip the camera around. And if anyone has any questions, if you want to go ahead and put them in the chat while I'm here with Adrian before I go back into the refrigeration unit, or it's cold again and I lose the internet. So John, if you could let us know if there's any, hopefully maybe some people are typing something in.
Looks like Wendy might have had her hand up. So if it's a small enough group, Wendy, if you wanted to unmute and ask your question, that would work too.
Thank you. That was clapping hands. So I'm just so giddy with what I'm learning from you all. Thank you so much. No question at this time.
Oh, you're welcome.
Great. I don't see anything else coming into the chat.
Who knew something that's playing
here's
around
one.
so revealing, right?
Here's one from Peggy. How do you get wind information from data you get from the sediments? How do you separate wind-blown sediment from terrigenous sediments via rivers?
That's really an astounding question. So we're drilling these cores right way out in the middle of the ocean, so we're not close to any rivers. So usually when river sediments get moved into the ocean where the river meets the ocean, that sediment's very heavy and dense. It doesn't get carried very far. Some of that very fine clay and silt, the really fine grain stuff, that can get carried far and kind of deposited. But in general, it doesn't make it out into the middle of the ocean basin. And that's kind of where these cores were drilled from, very far from land. Instead, what we look at is these heavier minerals like titanium, zirconium, and some other lighter minerals, so lower density like aluminum. And aluminum is very easy to transport via the winds. So I don't know if you all remember, in 2020, there was a Saharan dust storm. And this was kind of in the middle of COVID, so it didn't make big news, but there was an article about it. There's a dust storm in Africa, and from space, they photographed the dust move across the entire Atlantic Ocean, and it blew across North America. So there was like breathing difficulty, like people were having problems breathing because there was so much dust in the atmosphere in the US. And it was all from Africa, and it was all wind blown. So this wind, once these particles get caught in the upper atmosphere, they can get carried, these particles, really far distances. So a lot of what we're looking for in these cores are some of those lighter minerals or elements, so aluminum that can be blown in, and some of the heavier elements like zirconium, titanium. So the heavier elements like zirconium, titanium, they get blown into the middle of the ocean by very heavy winds or winds that are very sustained. And the aluminum gets blown in almost continuously, but when the winds kick up, we'll find greater amounts of it. The other part to answer that question is these elements don't occur naturally. Most of them don't occur naturally in the ocean. So we know that they're not there normally. Instead, they have to be transported in by the winds. That's how they're getting into this part of the ocean. But if we were near an area where we were looking at like nearby a river, it would be very hard to separate what's windblown versus what's carried in by the river system. I've never worked in a system like that, but I imagine it would be very tricky to separate those two processes using this method. So we're quite lucky that we're so far from land because we don't have to deal with parsing out what's windblown versus what's from a river. So yeah, that's a really excellent question. Happy to answer others if anyone has. You're welcome.
Great. No other questions in the chat at the moment.
Okay. Adrian, thank you so much. We really
No
appreciate
problem.
that.
Yeah.
And just a quick note, as I mentioned, we don't have these XRF scanners on the ship, but we do have PXRF, so portable scanners. And we are using one of them here right now. There's one that is on its second expedition now on the ship. We had one on my expedition. It was not working as well, but now new equipment on the ship. And again, it's depending on what we're looking for and what the objective is how we make sure we have that technology that we need to use. There is an XRD on the ship, so X-ray diffraction can be done, again, looking at the minerals that are present. But to get this elemental information, which is so valuable when we're doing paleo-oceanographic reconstruction or paleoclimate, it's really nice to have the scanner, and you're running 2 centimeters. Every 2 centimeters, it's touching down on the plastic is there again to kind of protect the scanner. So every 2 centimeters, and it's taking how long to run each of these cores?
About an hour and a half on this scanner, and not quite an hour and a half, like an hour and 10 minutes on this other scanner.
So it is long. It takes a while to collect data, but the data. So great. Thank you again, Adrian. I'm going to swap this around and we're going to continue on through the Gulf Coast repository now. So I'm going to be going back into the refrigeration unit. I apologize as I walk through. I will end up disappearing again once I'm in here. Hopefully you still have me a little bit. You can see some empty racks in front of me. So these cores right here are the ones from my expedition and the one right after. So these are ones that are here temporarily to get the scanning before they go to Germany. But this is it for empty space. The room we were just in with the 2 XRF machines, those machines will get moved and this space will be turned into more refrigeration storage. But there is an amazing collection of history here in this repository, and it goes back in time 170 million years. So it's exciting to think about what else we haven't learned from all the material that's here. So again, in terms of repositories, so exciting to see what's here. All right, I'm gonna now walk briskly through here and we'll continue our tour. Okay, John, am I back yet?
Yep, you're here. You didn't really leave except for a couple of skips.
Oh, wonderful. Okay, so you saw rows and rows and rows and racks and racks and racks, right?
Yep.
Wonderful. Okay, so in this area we have some of the members of our science party that are prepping samples. I'm not going to go into that back room, but I think maybe on the other side we can poke our head in where the rock cutting is going on. So to prepare these samples for scientists to either take with them on the plane or ship, as you can imagine, most people will actually take it on the plane with them. So they are marked and they are bagged and they are tagged again for to be able to bring to their home institutions or for colleagues of ours that aren't here just yet. I love this shark. I think it, you can't see what he's got in his mouth. It says core cutting zone. Inside that space right back there are 2 rock saws and also a drill press so we can collect some paleomagnetic plugs as well. So very active workspace this entire week, trying to pull material together so people can then bring it home and continue the analyses. So let's go ahead. We are at the end of our week. So this has been a week-long adventure for everyone coming from South Korea, coming from Japan, coming from Italy, coming from the UK, people that have, again, that were on the ship, but now are back together so that we can discuss a little bit more what we're seeing. Looks like the core is gone from here. So as we're at the end of the week, people have been incredibly efficient. Everyone's been excited. It's been long days going through and looking at this material. So I apologize, there's no core left in this room. But oh, we have these classic volumes. I don't know how many of your institutions now or when you were in graduate school, you had the lovely collection of IODP volumes, ODP volumes, DSDP volumes that are the initial reports and such. All of these are online now and available as PDFs and free download. So if you want to have students look up information from past expeditions, where they went, how much they collected, what they saw, there's also an image database online where students could look through that as well. You could do some great classroom exercises with that, putting it together. So again, all this has been funded by National Science Foundation. So it is available for you to use either for your own research or to be able to do exercises with students as well. I do see some stickers here, so at least maybe I could show this. Each scientist here gets a very festive colored sticker with their initials in it. One reason I think the phrase party is used. And so as we have the split cores, like you saw Adrian showing us the split sediment cores, if people want samples from a particular location, they'll put the sticker with their initials in it onto the core, and then those samples are then cut and packaged and again sent away. So I apologize, there's no hard rock core out anymore. It looks like they finished with the hard rock core. But what I will do is I'll come out here into the lobby. The other thing that's really nice is not just the images of the core, but the images from the ship as well. So every week during an active expedition, they have something that's called the Family and Friends Gallery, and you can go online and look at that. And so there's a selection of photos from what's happening on the ship. And it celebrates everything from the drilling activities to the birthday celebrations. I don't know if you saw that when I came by before. So a little bit more about an insight into what life is like on the ship and what the activities have been. So at this point, I will pause and see if there are any other questions that I can respond to, or maybe try to pull another scientist in if I don't have the answer. in case there's anything that's still going in the chat, I do want to thank NAGT for allowing this to be one of their webinars, because again, I think it's really helpful for us to be reminded of thinking about how to show students that whole continuous process of research. It's not just going out in the field, but there's a lot that goes on afterwards, and what do you do with that material afterwards? I think it's really important for us to share and showcase that as well.
So we do have one question from Wendy. Are rock cores processed and archived in the same way as the sediment, or any different steps?
So it's a little bit different. So all the cores, again, are split in half, and then before they go into refrigeration, they are sealed in plastic. It is a thinner plastic used on the sediment cores and a thicker one on the hard rock cores. The plastic for the sediment cores, it's pretty much the same quality as food wrap that you would have. And one of the reasons we wrap it in plastic before we put it in those giant D tubes is because you want to prevent desiccation and you want to prevent molding. You can't prevent that 100%, as we know, right? When we put food in our refrigerator and we wrap it in saran wrap or other plastic wrap, that still you can get mold and desiccation. But to try to minimize that impact, we'll use some plastic that's there.
No other comments at the moment.
Okay, that then John, that is the information that I've got to share. There actually is one more video link, John, that I emailed you. For any of you that might want to show your own students, maybe not this webinar, but a kind of a short video overview of the Gulf Coast Repository. There is a video that EarthScope did. They came down and they did an interview and have some great shots. So that YouTube link that's in the chat might be, if you're talking about scientific ocean drilling with your students, which I hope you do. There is so much that has come out of these missions exploring our ocean, and significant findings that are just the foundation of our discipline. So talking about the ship as well as where these materials go. And so that video, I highly encourage you to watch.
Great. Well, thank you, Laura. This was a great webinar.
Oh, looks like one other question,
Oh,
John.
go for it.
My experience as a science education outreach officer. So yes, so when an expedition is on the calendar that it's going to happen, then there's applications that open up for scientists to apply to join the expedition, either as a sedimentologist or a petrologist or paleomag. But there's also one or two what we call onboard outreach officers for every expedition. And that is a separate application process. And it is, you do not need to have a degree in education. You do not need to be a scientist. So they look for different people. It could be a freelance journalist. You could be an artist. And some of the duties, though, if you get selected to go on the ship for 2 months, is you are doing ship to shore broadcasts. So similar to what I'm doing right now, except you're carrying an iPad on a moving ship that's going up and down. So it's a little bit trickier, but you get to reach out with classrooms of all ages and grade levels from across the globe, which is a lot of fun. I know during my 2 months on the ship, I did 50 tours, but it was great. It was a lot of fun. In addition, you're also blogging about the experiences. And if you go to joidesresolution.org, you will see the blogs from from the current and the prior expeditions. You're also doing the social media from the ship as well. So you're doing Facebook, Twitter, and Instagram. And then you are also asked to come up and design your own project from the expedition. So what is it that you will do that is kind of a separate and unique? It could be some kind of curricular material. It could be some kind of multimedia material. So, and oh my gosh, the sunset's out to sea, totally worth going to sea for. So when I was on the ship, there were 2 projects I did that involved Google Earth, because I'm always looking for ways to increase the geospatial knowledge of our students. And so one was every day when I was on the ship, I put a place mark in Google Earth and a photo and description from that day, so people could see where we are and what we were doing. Huge hit with family members that thought we were so far away. Then I also did a voicemail project. And so I asked the scientists on the ship, if you were able to call home but someone didn't pick up, what message would you leave on the answering machine? And I also put that in Google Earth for the days and locations for where we were. So I like tapping into that. My post-expedition project is actually going to be, some of you may know that I'm a quilter and I do science-themed quilts. So I'm doing a collection of quilts based upon our experience from this expedition. So stay tuned to that. Hopefully by the end of next year, I will have that ready to go and share with everyone. So for the application, there is a call right now, actually, that is open for another couple weeks. So if you go to joidesresolution.org, you'll see there's 2 upcoming expeditions. They're searching for outreach officers right now. You fill out an application. If you are selected from that initial pool, then you have an interview with the co-chief scientist and the expedition project manager. So there's a lot involved in that selection process, but incredibly rewarding and absolutely worth it. And you have so much material you can then share with students, colleagues, your community for several years to come.
Great, Laura. Thank you so much.
Absolutely.
Yeah, so thanks very much for speaking, and thanks to everyone who participated today. Before we wrap, I wanted to remind everyone that the next webinar coming up from the NAGT webinar series is Thursday, November 17th, and it's entitled Evaluating Lessons Using the NSTA Sense-Making Tool. And you can find more information about that on the URL I'm about to drop into the chat. And then also, please take a moment and give us some feedback about your experience with this webinar at this second URL I'm putting in. Your feedback is really important to NAGT and to the series. We want to continue providing high quality professional development opportunities that matter to the community. So your feedback on this and all the webinars is very important. And so with that, I will say thanks again to Laura, and thank you again to everyone for participating today, and we'll see you next time.